Dr. Myler, we are here today to present a basic technology tutorial relating to U.S. patent number 5771238, which I will refer to as the Sutton patent. Would you please introduce yourself and give a little of your educational and professional background?
Sure. My name is Harley Ross Myler, and I did the beginning of my formal education at Virginia Military Institute, where in 1975 I received a Bachelor of Science in Chemistry with a double major in electrical engineering. Following VMI, I went into the United States Army as a missile systems officer, and after my tour I returned and went to graduate school at New Mexico State University in Las Cruces, New Mexico. And there I was awarded the MSEE, or Master of Science in Electrical Engineering, and that was in 1981. And then in 1985, I received the PhD in Electrical Engineering. Okay. And following New Mexico State, I worked in industry in various engineering jobs and positions. And then in 1986, I joined the faculty of the University of Central Florida in Orlando and spent 16 years there, and that was as a professor of electrical and computer engineering. Went through the ranks of assistant, associate, and full professor there. And then in 2001, I came to Beaumont, Texas to join the faculty of Lamar University, and I took the job of the Department Chair of Electrical Engineering. And at that time, I became the inaugural holder of the Mitchell Endowed Chair in Telecommunications.
I understand that you've read the Sutton patent, which is at issue in this case. What is the general area of technology that is related to the Sutton patent?
Well, the Sutton patent generally relates to the transmitting of electronic messages, and in particular transmitting data over a one-way radio system. It extends to 7-bit ASCII networks, 8-bit and binary data transmission capabilities, and it provides for an over-the-air encoded security management and control system for remote units and on either type of network, the 7-bit or 8.
I understand that you've read the Sutton patent, which is at issue in this case. What is the general area of technology that is related to the Sutton patent?
Well, the Sutton patent deals with electronic messaging. And if we look here on slide 2, that's basically transmitting information electronically by wires or radio signals with integrated encoding and decoding equipment. And that's really the substance of this patent. And it relates to a lot to the hardware, and we're going to see that as we talk about this. And what that does is points us to a timeline of the development of hardware and ultimately the development of messaging and these coding things. And if you look here on the slide, I've put down some of those things. Obviously the simplest and earliest, looking at the cavemen and things like that, is the notion of signaling with fires, lamps, sounds. This is what we might call the pre-electromagnetic age. Then the beginning of electronic messaging was essentially the telegraph, and it was a simplex device, which means it's one-way communications, and it was a coded messaging, in other words, with Morse code. We then came up with the telephone, which allowed us to have a more rich and robust messaging in that we could now transmit voice over great distances. And it was duplex and simultaneously two-directional. Then radio came along, and of course one might argue that this was the true electromagnetic, because now we were using radio waves, and it incorporated simplex, duplex, and multiplex capabilities for data, voice, and now video, the idea of video. And then to what this patent speaks to, and that is beepers, pagers, cellular phone technology.
Okay. What are some of the things that are needed when you're transmitting an electronic message?
Well, if we look on slide 3, what I've done is shown some of these components and how they come about to affect electronic messaging. And what we've got here is sort of now graphically that timeline, the telegraph and teletype. We've got a wire. Radio and radio telephone, we've got antennas transmitting information by radio from point to point. And then we come to the idea of a network system where we've got beepers, cell phones, and both of these include facilities for what we call texting, which is text messages and text messaging.
Is there some way that that information is encoded when you're sending these types of electronic messages?
Yes, in fact, there's layers of coding, if you will. Mm-hmm. And if we look on the next slide, this is slide number 4. What I'm showing here is the idea of character coding and some examples. Here we've got the word ASAP, and of course that in itself is a code. It's an acronym, and it means as soon as possible. And also what I've included with this example is it's not only a coded acronym word, but I've also included a symbol that indicates the exclamation point, indicating that it's hurry and do it right away, and there's some urgency involved. So we have a really nice coded symbol that pretty much everyone understands. And if we take the word ASAP and want to transmit it, for example, through a telegraph system, we would use Morse code. And there I've shown to the right ASAP encoded in Morse code. Now you say, well, wait a minute, there's only 4 sets of codes of dots and dashes, and that's because the original Morse code didn't have an exclamation point. So in a way, the exclamation point was like a forbidden character or a prohibited character because it didn't exist. Then as we move up into the idea of teletypes and computer type data and texting, if you will, early texting, we come to the Baudot code. Baudot code was a 5-bit code, and there you see ASAP represented in Baudot, and you'll notice ASAP is the first 4 blocks in the 5-bit code, and then there's a figure shift code which allows for the exclamation point, which doesn't exist in Baudot code, but when you put the figure shift in and then send the letter F in Baudot, that means exclamation point. So now we're seeing a coding that allows for characters that aren't allowed in the code or aren't present in the coding system except through a separate mechanism, the idea of an escape code. And then finally what I'm showing there is ASCII code, and I'll talk a little bit more about that in detail, but now we see that in this representation we have a 7-bit code, and ASCII indeed includes a coding within the system because it's longer, includes a code for the exclamation point.
You've used the word bit a lot in this explanation. Could you explain what do you mean by bit?
Well, that's I've illustrated that on slide 5, and it'll make it a little bit easier to understand by looking at that. Bit is a contraction of binary digit, and it represents a single bit is what we call binary word, and it represents 2 states, a 0 or 1. We see that at the top. And this is related to this notion of coding, and earlier on the previous slide I was talking about coding in the sense of more bits, more data. And so here we have also in this slide in the middle, a 7-bit word. And now we have seven bits. Each of those has 2 different states, 0 and 1. So combinations of those 7 bits allows for 128 states, or we could represent, for example, the integers from 0 to 127. If we add another bit, we essentially double each time we add a bit, so it's an exponential relationship. But now we have an 8-bit word at the bottom, and that's going to allow us 256 states, or from 0 to 255. And of course the 8-bit word, we have a special name for it, and that's the byte.
So the number of bits has a direct relationship on the total values that can be represented by that group of bits.
Yes, that's correct. And if we turn to page 6 or slide 6, there's a table showing sort of a progressive table there where we go from 1 bit, 2 bits in the first column to 3 all the way to 7. And we're going to have 2 possible values, as we mentioned. If we add another bit, it's going to, the 2 bits is going to give us 4. And we see the numbers 0 to 3, and then the binary representation, and then 3 bits and so on and so forth up to 128 things with 7 bits. What this means is those values can now be associated with specific characters in the set. So if we're only working with a 3-bit word, we can only represent 8 different characters, if you will. Whereas if we work with 7 bits, we're up to 128.
Earlier you mentioned ASCII. Let's try to get into a little more of what 7-bit ASCII is.
Well, ASCII stands for the American Standard Code for Information Interchange. And graphically, a graphic example is on the next slide, slide number 7. And what we're doing is in the character set associating it with associating a value with a particular character. And here I show an 8-bit word, and that 8-bit binary word is the number 65. Well, the number 65 in the ASCII character set has been assigned to the capital letter A. And all of the codes, all through from 0 to 127, are assigned to different letters and symbols and so on, and also some control codes. And what's significant here is that this is an 8-bit word, and the most significant bit, which is the 0 to the far left, is a 0. It actually isn't needed in a 7-bit representation.
Earlier you talked about radio transmission of messages. What are some examples of transmitting messages using radio transmissions?
Well, as I mentioned earlier, beepers were commonly used to receive short text messages by radio transmission. And this is sort of illustrated in the next slide, slide number 8. What I've shown here is some different devices. And in the upper left-hand corner, that's your standard beeper. And it has a display that you can't see directly on the top of it. And essentially, its functionality is to receive a telephone number. It would beep, and that would say a telephone number would appear, and the indication was you were to call that number. And you know, in television series and stuff where people have these beepers, if you've never actually owned one, physicians and other professionals look down at the beeper and, oh, I need to call my secretary, or I need to call my office, because they recognize the number. But the beepers were restricted just to numbers. And later on, texting was allowed. In other words, you could receive a short message. And that's shown with the device in the center at the top on the slide. You see now a message maybe from a friend saying tickets are now on sale, or even from Ticketmaster if you've told them, let me know when the tickets come on sale. And so these beepers and these early text messaging devices were limited because of the hardware. They were limited because of the way the messages were processed by the retransmission stations and things of that sort. They still included computer controls to handle the button pressing and certain logic that took place in it. But again, they were limited. Now, if you look at the device at the top on the far right, that's a more advanced messaging device. And you can see there's graphics and much more sophisticated information. And then we come down into the middle of the slide at the bottom, and we've got an iPhone, possibly right now the most sophisticated of messaging devices, because now you have the option of creating very complex messages, graphics, video, and so on, way beyond the limitations of text.
I'd like to get into a little more about what you mean with the term sophisticated information.
Well, computers have the ability to manipulate information that goes beyond just numbers and text. They can go all the way, if you will, to graphics, pictures, video, and sound. And what the Sutton patent recognized was that people wanted to be able to go beyond simple texting. They wanted to have this more robust data, this more sophisticated data. And there was also a desire to encrypt data to protect the message in passing, because there may be sensitive data that they didn't want to get out. All of this required that binary information be transmitted. Now you may think, binary information, isn't that what we've been talking about? No, we've been talking about very restricted binary information. We've been talking about character sets that are, their range is dictated by a binary word. what I haven't mentioned, which was sort of in the background, was that certain binary patterns were also reserved by different systems for control functions and other things of that sort. When you increase the sophistication of data, you require a larger range of binary data for representing that information. And this is what the Sutton patent anticipated, was that because of that increase in that range of data that would be required for these added enhancements to the existing texting facilities, problems would arise with the fact that these binary codes that may be used for other things other than the user's information might cause issues within the system.
Now, the Sutton patent talks about 7-bit and 8-bit information. Could you explain a little bit about why that's important and what the differences are?
Well, the 7-bit, 8-bit differentiation, if you will, has a lot to do with the fact that the early systems evolved with increasing number of bits in the character set. For example, with the Morse code, we essentially, for every character, we have a collection of dots and dashes. A dot and a dash constitute a single bit. If the bit's 0, it could be a dot. If it's a 1, it's a dash. The Baudot code came along because now we wanted to be able to, with machines, the teletype, be able to differentiate different character sets and so on. And so we needed a more robust code. With the advent of the computer and teletypes being used as input devices into computers, we had the need for an even more robust coding, and that brought on the 7-bit ASCII code. Now you may say, but wait, why didn't they just go all the way to 8-bit? Because those teletypes preceded the use of computers. And so the 8-bit standardization as 2 4-bit nibbles going into a single byte didn't come along until later. So the 7-bit code was a natural progression beyond the Baudot 5-bit. We've got the 7-bit word, a 7-bit word at the top, and there you see the bit patterns which represent the ASCII code for a lowercase g. And in an 8-bit word or a byte in a computer storage system, there's an extra bit that's essentially unused. And so there we have sort of the dividing line between why the 7-bit and why the 8-bit. And that's a very, very important point, because it led the Sutton patent to a number of innovations that allowed these texting systems to get past some of the limitations of the hardware.
The Sutton patent talks about stuffing and 7-bit and 8-bit characters. Can you give us an example of this?
Well, this is one of those innovations that I was talking about. If we now look at slide number 10, we see an example of the packing of 7-bit characters. The 7-bit characters are coming in, let's say, for example, on a radio wave through a radio system, and it's a sequential 7 bits are coming through. And of course, we enter into the question of, at what point do we know that a character is passed? And if a priori we know we're working with 7-bit characters, it's very easy to look at the first 7 bits and then the next 7 bits and the next 7 bits, which represent those individual characters. However, when we get to the computer, and it's literally the computer in the handheld device, or potentially the computer that's located at the messaging center or something of that sort, we now have an 8-bit system. Everything is done in 8 bits and combinations of 8 bits, or 8-bit words, or 8-bit bytes. And so if we were to transmit the 7 bits using an 8-bit transmission system, we would be wasting a bit on every character transmission. And so what the patent describes is the stuffing of the 7 bits into an 8-bit word. And in this illustration in the slide, I show that there are 7 8-bit words, and those are delineated by the vertical blue lines. And those 7 8-bit words allow for 8 7-bit words to be packed into them. In other words, we gather an extra 7-bit word because we're taking advantage of that extra bit each time. And we're sliding the successive 7-bit character bit pattern into that extra bit. And each time it slides in, it opens up another bit as we go along. And that's why I show the sort of stepwise staggered representation.
Now, the Sutton patent also talks about unpacking. What is an example of unpacking?
Well, that's just the reverse operation. And there I show the reverse on page 11. Again, we have the 7 8-bit words at the top. They're coming down and getting packed into 7 8-bit words being packed into 8 7-bit words. Those 8 7-bit words, when they show up at the receiver, the receiving device, have to be put back into the storage containers, if you will, in the memory of the computer, which are going to be 8 bits. And so they have to be unpacked, and now what you see is those 8 7-bit words now become 8 8-bit words at the bottom. And what I've indicated with a little empty square there is that extra bit, and the red line with the 2 dots indicates the 7 bits in each case. So there's this expansion process that takes place as a part of the unpacking process.
The Sutton patent also talks about prohibited characters and handling them. Can you give us a brief explanation of what this is?
Well, the idea of a prohibited character is one that it's a character that should not be part of any message for any number of reasons. And when I say part of any message, I mean the user-generated message. In other words, there are places where a particular character are not allowed to occur. And it could be because of hardware, software, there's any number of reasons, the coding schemes in use. And what you want is the receiver to accept any message that the originating user is going to create. And so if there are characters which, because of the nature of the data that the user is trying to transmit, has the potential for prohibited characters, you want a mechanism by which to accommodate that in the system. And I've shown an example of what we might consider a prohibited character using the previous example. This is in slide 12. What we have there is a text messaging system. It has a keyboard and a display. And what we're transmitting is the word ASAP with the exclamation point. And I've said, let's just assume that the service hardware doesn't recognize that exclamation point. It'll receive the A, the S, the A, and the P, which are fine. When it sees the exclamation point and it's not expecting it, then that can cause issues. It can cause the system to reset. It can cause the system to reject the message. Any number of reasons in existence because of the nature of these systems. That then becomes a prohibited character.
Dr. Myler, what else does the Sutton patent talk about to bring these concepts together?
Well, it talks about what we call packet preparation. And this we see illustrated on slide number 13. And essentially what packeting is putting data together in a structure so that it can be transmitted and through a particular system. It'll be accepted by the receiver, and it'll be properly